All right, everyone. Welcome to the next lecture in the Nucleophilic Substitution and Elimination series. And today we are discussing the third factor that is going to affect SN1 and SN2 reactions, and that is the nucleophile strength. So let's get started with this. Now, the biggest takeaway that you want to have for this lecture deals with negative charged nucleophiles versus neutral nucleophiles, specifically the negative versus neutral. And that's what the first half of this video is going to discuss. And then there are other factors regarding nucleophile strength that we will discuss. But negative versus neutral is the biggest takeaway by far. So what do we mean by this? Let's use a general example. If you were to look at, let's say, OH, right? So hydroxide would be considered a negatively charged, right? It's an anion nucleophile versus its counterpart, which would be water. So this would be considered a neutral nucleophile because there's no charge. So when we say neutral, we're talking about the fact it's not a cation or an anion. All right, now sometimes when you see negative charged nucleophiles, the term hard is used. So they'll say this is a hard nucleophile versus something that would be considered a soft nucleophile. Okay, and you can kind of view this as the aggressiveness or the energy of the nucleophile. So when we have something that's considered a negatively charged hard nucleophile, there's a couple of things. First, it's going to have high energy. So we're even talking about if you were to look at free energy diagrams with the basically standing energy at the beginning as a reactant, it's going to have higher energy than that of water. Okay, and because it's going to be higher energy, that means that we would most likely, in all cases, see it acting more reactive towards any type of alkyl substituent with a leaving group. So this is important because when we're dealing with SN2, we only get partial positives. We don't have formal carbocations, and because these are more aggressive, they are more reactive, a partial positive is enough to attract these types of nucleophiles. And so it turns out that the negative hard charged nucleophiles are beneficial more for SN2 than they are for SN1. So obviously that means SN1 is going to be neutral. So what is it dealing with soft nucleophiles that SN1 tends to prefer? Well, they are lower energy, and keep in mind that when we have an SN1, the rate limiting step is the leaving group leaving. It does not have to do with the nucleophile. In fact, if you look at the kinetics, the nucleophile does not come into play because it's just the formation of the carbocation, and then the reaction in the snap of a finger is basically over once that happens. Right? Now, in turn, because these are sort of mirror images, right? This means it's going to be less reactive. Now, a lot of students see this and they think, oh, well, that's a bad thing. Why would you want a less reactive nucleophile? It still has to participate. Again, in the rate limiting step, you want the leaving group to leave without interference. You don't want a nucleophile coming in. Once you have the carbocation, you can have a less reactive nucleophile and it will still be more than sufficient to get the job done. And the reason for that is that you have a carbocation. Carbocations are formal charges, right? And so a carbocation is going to be enough to draw in this weaker, less reactive nucleophile. It won't have a problem at that point, right? So let's look at SN2 and SN1, just the general mechanisms again. So in the case of SN2, you have some alkyl group and leaving group, and we've discussed in the previous lectures the position, the optimal positions for these leaving groups, as well as their identity for these reactions. So during the transition state, you're going to have a partial positive buildup of charge on this alkyl substituent where the leaving group is, right? And then you'll have a partial negative buildup as this leaving group starts to take the electrons from the covalent bond. So in this case, you're not going to form a formal carbocation. There's not enough hyperconjugation and other stuff. So the nucleophile, you want one with a negative charge that's higher energy. You want something that's more aggressive that can come in as the leaving group is being displaced. So we have a weaker positive buildup. Okay, so that's an important part here. We have a weaker right? Partial positive charge. It's not going to be a formal carbocation. And because of that, we need a stronger nucleophile. We need one that's more aggressive, that can sense that just partial buildup. All right, there's other things to consider. We have sterics here. Sterics, okay, will tend to hinder a reaction. So why do we have sterics? Because the leaving group has not left yet. It's on its way out, so it's still present. So if you have something that's sterically hindering, you need a more aggressive high-energy nucleophile. You don't want a weak one where the steric hindrance is going to keep it at bay more, all right? And then because of these, you have this nucleophile acting more aggressive, and it can get the job done in an SN2. All right, so now what about SN1? So we know that when we're dealing with SN1, we have the leaving group. It's going to leave, and when it leaves, we're going to be left with a carbocation on the alkyl group. And when this happens, we can afford to have a weaker nucleophile that does not have a negative charge come in and attack that carbocation. And then, of course, we end up with the nucleophile attached. Okay, now this is important because in this rate-limiting step here, the fact that we have a weaker nucleophile means it's going to be less aggressive. And if it's less aggressive, it means it's not going to interfere nearly as much as a negatively charged nucleophile. And that's important because this is the rate-limiting step. What we're going to do is we're going to wait for the carbocation formation. And at that point, after we have the carbocation formation, then the weaker nucleophile can come in. But we don't want it attempting to come into that partial positive charge, particularly if we've got more buildup, because in an SN1 we've got more tertiary and secondary type structures for the leaving group, right? We don't want that interference. We want the nucleophile kind of waiting out on the sidelines until the optimal moment, and that is when it will strike. So we do have some other considerations that we want to talk about, but first I just want to recommend that everybody head over to chemcomplete.com. So chemcomplete.com is our main website. You've obviously been hearing me talk about it if you've been in tune with the other videos. We do offer services here, so if you are struggling in your class, you can get one-on-one tutoring and mentorship from me. You can request a personalized video lesson if I haven't addressed something on YouTube or you need something very specifically tailored to your interests. And then, of course, we have the guides here. The guides are $5 a piece. We do have a Nucleophilic Substitution and Elimination guide for $5. It comes with all of the details plus more that we're going over in this free YouTube course. And you will also get an entire set of practice questions with full walkthrough answers. Okay? There's some others here, and we're constantly working on it. So head on over to chemcomplete.com. You can check these out. We've got a free resource page. You can contact me. And that would be a wonderful way to support the channel. So let's get back to the substitution lecture. Okay, so other things to consider regarding what's called nucleophilicity, which is how strong a nucleophile is going to behave. So electronegativity is a factor. And in general, as electronegativity is going to increase, we're going to see that nucleophilicity is going to decrease. This is a common trend. Now, there is an exception to this depending on the solvent you use, and we're going to talk about that next. You can see I have solvent effect listed here. All right, but in general, as the electronegativity increases, the nucleophilicity decreases. And this kind of makes sense because if we think about electronegativity, it's the greediness or the ability to hold on to electrons. So if we're talking about electronegativity, right, I would expect something like fluorine to hold on to its electrons very tightly. It's looking for electrons, right? And if you look at atomic radius size, those electrons are brought closer to the nucleus. They're held very, very tight by those protons. So they're not as likely to give them up in a reaction or donate them, and that's exactly what we need from a nucleophile. A nucleophile has electrons that are going to be sent out and donated in a reaction, okay? So, for example, let's pick a row and go across. So let's say that we had a carbanion, like a CH3, and then we had an NH2 anion, right? And then we had an OH, okay, And then finally, we have the fluoride ion, right, which also has a complete octet there. So when I look at these, I would consider the methyl anion to be the strongest nucleophile, right? It's the most willing to donate this set of electrons and get involved in a covalent bond. Then the amine, then the hydroxide, and then finally the fluorine would be the least of the bunch, right? And this also kind of makes sense because we said the halogens are good leaving groups. They tend to be unreactive. They tend to hang out in solution. Now, fluorine wasn't a great leaving group, but you can still see the general premise here is that the reactivity, okay, the less electronegative we are, the higher the reactivity is going to be in terms of a nucleophile. So we would expect that this would be the higher end with the methyl anion going first, and this would be the lower end. We wouldn't expect fluorine to be a very good nucleophile in this case. Now, there is a solvent consideration here. So you have to keep in mind that solvents are going to play an effect, and factor 4 is going to be solvents. So our entire next lecture is going to be talking about solvents and their importance. But we have two different types of solvents we work with when we get into these types of reactions, and that is a polar protic solvent and a polar aprotic solvent. So a polar protic solvent, and again, this is going to be covered in far more detail in the next lecture. A polar protic solvent has the ability to hydrogen bond, so it's any type of solvent with OH or NH. So your amines, your alcohols, water, those types of things, okay? And if something is polar aprotic, it's going to be just the opposite. It has polarity, however, there are no OH or NH bonds. Now, that being said, that doesn't mean there can't be oxygens or nitrogens. There can be. You just can't have a hydrogen attached to them, like in the case of an alcohol. But you could have, for instance, a ketone. Something like acetone would be an aprotic solvent. All right. Now, this will affect the factor we just talked about. So, as electronegativity increases in a polar protic solvent, the nucleophilicity will decrease. So, as electronegativity increases, okay, the nucleophilicity will decrease for polar protic. Now, in the case of polar aprotic, you're then going to look at, as electronegativity increases, the nucleophilicity will also increase. Okay? And that really has to do with hydrogen bonding. Hydrogen bonding is very important in SN1 and SN2 reactions, and it goes beyond the scope of just the nucleophile, but we will talk about that some in the next lecture. So what's going on here is in a polar protic solvent, let's say that you've got something like a fluorine that's got these electrons. Okay? There is hydrogen bonding that can occur that helps to stabilize this fluorine atom. So when you start stabilizing, okay, you can view this kind of as steric hindrance, right? The more water molecules that come around, it slows the nucleophile down. All right, and it also affects how reactive these electrons can be, because the stabilization is going to lower the energy, and when a nucleophile has its energy lowered, it's going to become less and less reactive. And so therefore, the things that are the most electronegative are going to be drawing in that stability more and more as far as the polar protic solvents are concerned. So if this doesn't make a ton of sense, wait until the next lecture and make sure you watch that, okay? And it should clear some of it up. But for right now, know that polar protic solvents, okay, any solvent that can hydrogen bond, that's going to make it that as the electronegativity increases, the nucleophilicity decreases. All right? Now, for sterics, this is the last consideration. As we start to pile up, okay, steric hindrance, so I'm going to use charged ones in this example. Let's say hydroxide, and then let's say we have a methoxide ion, so a CH3, right? As you start to pile up these steric considerations, you're going to hinder the nucleophile in its ability to approach. Because remember, nucleophiles have to come in and interact with wherever the leaving group was. So in an SN2, it's going to be very critical because you have to get in as the nucleophile is there, and then, as the leaving group is there, and then for an SN1, you're talking about having to come into the carbocation. Now, the carbocation in an SN1 is not as sterically hindered, but you still do have other alkyl groups surrounding that carbocation, and so you want to consider that. So as we continue to increase in bulk, we end up seeing that the nucleophilicity decreases, right? Because these get harder and harder to bring in and bind to an already somewhat sterically hindered position. So hydroxide would be the most reactive nucleophile, and the T-butoxide over here would be the least reactive, right? Moving along in this direction. So I would expect hydroxide to be the best. Methoxide would be okay, but it's starting to get more sterics. And then as I look at the isopropoxide here, this is getting even worse, and then the T-butoxide, right, is horrible. So we're basically having high reactivity on this side, and then we have low reactivity over on this side. So the general premise is, as branching and steric hindrance piles up, it's going to be worse and worse for your nucleophile in terms of its reactivity. So that is it. That covers factor 3. And again, I want to come up here and highlight the biggest takeaway is looking at negatively charged nucleophiles and neutral nucleophiles. And pay attention, make sure that you realize if you're being handed some sort of a salt. Okay, so if you have something like NaOCH3, this is not neutral even though it's written this way. When you put this into solution, it becomes Na plus and OCH3 minus. So this would be more beneficial for an SN2 reaction. So just pay attention to small details like that. Okay, the negatively charged nucleophiles prefer SN2, and the neutral nucleophiles prefer SN1. And then within those groupings, we have electronegativity, solvents, and sterics to be concerned with. That wraps up everything for factor 3. Thank you as always for learning with us. Comment if you have any questions or if you just want to leave general support. Like the video if you found it helpful. And of course, subscription will always get you up to date with the newest information. Head on over to Chem Complete and we will see you guys next time. Thanks for learning.